Hello and welcome to the sixth part of hexagonal multi-pattern lesson in Grasshopper. In this session, we will continue from where we left off in the previous part. We finished our planar hexagonal grid of points, add additional weavings inside the hexagons for quads and triangles, and assemble switches and modes. And the script, let me remind you, is meant to generate a seamless hexagonal pattern across multiple surfaces. Today we will move forward and learn the process of mapping objects from Cartesian coordinate space onto a UV space of a surface, as well as principles of NURBS surface construction, data streaming, and domains. Basically everything we need to achieve our desired goal in the future, pattern across multiple surfaces. Now, this lesson will be pretty heavy on theory, and I will deviate from our script to explain things. I will turn our script off for now to give some space in the viewport and start with curves, as they are the base building block for the surface and stream very important properties we will use. So this is the script we already built. And as always, you can go into the description to this video and download the script if you want to follow along. But we actually don't really need this script. They need our script for this session. So what I wanted to turn it off temporarily, not just hide it, but completely turn it off. How we're going to do that? Very simply, I will select the whole script. I will click middle mouse button, and while I'm holding the middle mouse button, I'm hovering into this icon and releasing middle mouse button like this. So now, as you can see, everything, all the wires become to be orange. That means there is no data passing through them, like literally no data. So it's not compiling. Okay, I can of course turn it on in the next lesson or in the next session. Okay, so next I will scroll out, because if you remember, we worked with a very tiny sizes. Our pattern is normalized for reasons. So for now, we'll just scroll back and I will construct a curve. So to do that, I will use this tool in Rhino, which is called control point curve, and just construct a curve through a few points. For example, here. Then I will click enter, and as you can see, I have myself a curve. Now what I want is, I would like to visualize a control points. So I click on the curve and I will type F10, and this is the default hotkey. So basically my control points are visible for the curve, even though the curve is deselected, right? Okay, so let's just zoom in a little bit and inspect our curve. Now there's a very specific instruments to inspect your geometry, and every CAD system have a bunch of their own. And Rhino of course has its own, and we will inspect it. But before that, let's try to analyze the curve just by how it looks, how many control points it has, and predict some results, because some of them are very logical and you can actually tell a lot about the curve without even inspecting that. And all which I will kind of specify here, I will basically create a list of my observations. All of them will be important for things to come. So first of all, what can I say about this curve? I'm gonna say that this curve is an open NURBS curve. Right from the get-go, I believe this is obvious. This is an open NURBS curve, or ONC. Why it's open? Well, because it's not closed. You're gonna see that the beginning and the end are not, connected. So this is definitely an open NURBS curve. What else can I say? Well, it has 4 control vertices, 0, 1, 2, 3, right? Makes sense. 4 control vertices. Next, now because we have 4 control vertices and this is a control point NURBS curve, I know that the amount of control vertices which we have for a curve is below the threshold by default for this for Rhino and this tool to construct spans, or more than one span, meaning that this curve is effectively a single span curve, which I will actually specify. So it will be a single span curve. What else can I say? Well, because it is a single span curve and it has 4 control vertices, it's absolutely 100% true that this is a 3-degree curve. So let me specify 3-degree curve. Right, what's next? Now, once again, because it is a single span curve, it has 3 degrees for control vertices, we have 2 vector nodes. Not 3, not 5, not 10, we have only 2 vector nodes. Now, there are only 2 because the span is only one. One big span has beginning and the end, and this beginning and the end are vector nodes. So I have 2 vector nodes. All right, now what next I can say? Now, because this is a single span curve, the parameterization of the vector nodes and the parameterization of the curve, the proper term will be the vector nodes parameterization. The vector nodes parameterization is uniform. This is a standard. If you have a single span, then the parameterization of the vector nodes will be uniform. So I will type uniform parameterization. What else can I say? Well, I can say that this curve is clamped. What does it mean? You see, if you look at the curve, it starts where the first control point is and ends where the last control point ends. So it's effectively clamped at the beginning and the end. These control points are not clamped because they're not coincident to the curve, which is standard. So safe to say that this curve is clamped, and yes, it is. So clamped at start, come on, and end. All right, cool. What else can we say? Well, because we have 2 vector nodes, we have a uniform parameterization. It means that the vector nodes themselves have a very specific values, meaning that the beginning and the end of the values are very, very specific. And because it is a uniform parameterization and this is a single span, I know that the values for them will be 0 and 1. So the first vector node will starts with the value 0, the last vector node will starts with the value 1. That's what the uniform parameterization is. It represents the vector nodes through integers 0, 1, 2, 3, so on and so forth. The more spans we have, the more numbers it will get. It will just linearly rise 0, 1, 2, 3, so on and so forth. We have only one span, 2 vector nodes, so first one will be 0, the next one, the last one, sorry, will be 1. On top of that, I know that this is a single span, 4 control vertices, and this is a clamped curve, so the curve must go through the first one and must go through the last one, which means that the representation of the vector nodes is supposed to accommodate that for the actual calculations. So because we have 4 control vertices, 4 control points, we need to basically all the derivatives of the formula, which is position, tangency, curvature rate, supposed to be clamped, meaning that the actual vector node will represent itself as a set of numbers. The first vector node will be 0, 0, 0, 0, and the last one will be 1, 1, 1, 1, like this. All right, now this is actual representation of the vector nodes, the actual span between 0 and 1, and as well as our curve. What's next can we say? Once again, still not really inspecting it, just looking at the curve. Now the next thing which I can say is that because our vector nodes, because of a uniform parameterization, in fact it is a single span, they start from 0 to 1. This curve has a domain which called the geometric domain, which mapped the same through the vector nodes, meaning that the geometric domain of this curve will be between 0 and 1, like this. And this is a geometrical domain. This is extremely important parameters for us. Once again, I will explain most of that later, just in a second. So this is the geometrical domain. What else? Well, I would say there is one thing left, and this is another domain, which can be somewhere from 0 to a number I can't predict until I actually inspect the curve. So I will say x, right? X. And this domain will be parametric. Oops, just zoom in. Parametric domain. Let me highlight it. Oh, sorry, underline it as well, because this is another extremely important parameter. All right, so before I explain what all this mumbo jumbo is, let me go in, select the curve, and inspect it. In Rhino, you can inspect your geometry, being curve, mesh, surface, B-rep, or polysurface, or whatever, through the command called what. So I will just literally type in the command prompt what and hit enter. And it gives me this object description window. Now, I don't really care about all of this stuff. I'm looking at this section. That's actually where the curve is described. Let's take a look. So it says that it's a valid curve. Well, good to know. I'm really happy that it's a valid curve. That's great. The next one, Open NURBS Curve. Yes, it is an Open NURBS Curve. It starts, it has start and end, something I actually forgot to mention. So the start is the actual position of first control point in Cartesian coordinate space, meaning x, y, and z, and the end is the last control point position in Cartesian coordinate space, x, y, and z, right? Okay, and what else do we have? Degree free. Yeah, we already figured it out. Degree free. Control points, non-rational, count 4. Now, I literally forgot to mention that the curve is non-rational. It can't be rational because this is not a conic, meaning that the weights for every control vertex is actually equal 1. They're not different. The count is 4, meaning that we have 4 control vertices, right? Self-explanatory. Now, what else do we have here? We have information about the nodes, and they are uniform. I already said that this is a uniform parameterization. Now we have a clumped at start and end. Yes, indeed, it clumped at start and end. But then similarities changes. You're going to see that I have information about my vector nodes, amount of vector nodes, the actual description of the vector nodes, and geometric domain. Instead, I see delta and domain 0 to not to 1 to some number. What is this? And where are the other information? Now, this delta is the body of the domain, of this domain, and this domain is not geometric domain. This is 0 to x. It is a parametric domain. And as you're going to see, we don't see vector nodes, we don't see geometric domains. Why? Well, that's because the amount of vector nodes is something we can say, we can set, dynamically or not, but for example, the actual description of the vector node as well as the geometric domain is a properties of a curve itself. So without them, curve is impossible to construct, and they defined by your degree, amount of spans, amount control points, a type of a uniform parameterization. So they are drivers, they are consequence. And so important consequence that we actually don't have access to that. We can't change that. Some system, like Callias, give you information about geometrical domains. ICM and CTIA give you information about geometrical domains, but none of the systems give you ability to change that because they are consequence, not the cause, right? So, and that's, you're going to see in the Rhino, because Rhino don't even bother to show you that. What it shows you instead is another domain which is called parametric. And to understand why and it's actually, what's the deal with all of this, we actually need to quickly understand how the curve actually constructs. And I remind you, all of this is really important for what to come. So I remember that we need to construct a pattern across multiple surfaces. So just stay with me here. So the curve, I will avoid really heavy formulas and explaining of basis functions and the details. So just very, very primitively. Curve constructed through just very simple formula, which is actually much more complex. It looks like this. So C of t is it is a function of t is a parameter. We'll talk about this t a little bit later. Will be equal to basis function. I will call it BF, although in mathematics basis function described differently, just will be easier for you to understand. Basis function of t 0 in the power of 3 multiplied by first control vertex, this one, it will be 0.0, plus basis function of t, same mystical t, 1, it is a different basis function in the power of 3 multiplied by 0.1, plus, and so on and so forth for all control vertices. So what this formula actually does, and what are the basis functions? Now, the basis functions are mathematical functions to the specific power, calculated to the specific power, which basically describes how much every particular control point takes effect on constructing of the curve. In other words, you're going to think about that this way. Every point has a voice. And because this curve is non-rational, the voices here are identical. This loudness of the voices is identical, right? So every basis function describes the effect of the point through its voice, which is by default is the same on the curve. Like this curve at the beginning basically shouts, come to me, like pull the curve to me, I'm in control. And when this one is really very active and loud, the further away you go through the other control points, then fainter her voice will be, and more louder the voice of the other control vertices. Like for example here, this control vertex is at full effect. It has a maximum control. Everything else has some control as well, but it diminishes, the further it is away. And basis functions basically defines that. They defines that how loud the point's supposed to be along the curve between the control points. And this between control points and the position at which point it loudness is which, defined by this value t. This t, called a geometrical t or t parameter or t geometrical parameter. And if we look at our description here of our curve, we actually see this t. This t is the value within the geometrical domain. So this is a t geometrical, I'll put it this way, extremely important parameter. So this t geo sits within the geometrical domain, and geometrical domain described by vector nodes. So here you're going to see that we have a value within this domain. And let me remind, what is domain? Domain is a set of numbers, limits by its bounds, right? So this is the first bound and the last bound. How many numbers are between 0 and 1? Well, mathematically speaking, infinite amount, 0.1, 0.001, 0.0001, 0 point to the 10 to the power of minus 100, whatever. It technically infinite. Of course, in practice, in computers, it's not the case. Well, first of all, our computers works in 62-bit floats, so we're going to say that theoretically speaking, computer, it is possible for computer to, create a quadrillions of numbers there, like a lot. But of course, it's impractical also, because when it comes to the actual calculations, actual CAD systems, the actual sampling rate, and this is what the actual values within, is actually much, much, much smaller, and it's defined by the tolerance of your document. So the tighter the tolerance, the more calculations there are, the more t values there are, the smaller the tolerance, the looser the tolerance, better say, the less amount of t parameters there are. You don't have a full control, you control it through the tolerance, through the positional tolerance, because that's what it is. Right, so basically imagine that we have a set of numbers, and the set of numbers 0 to 1 basically parameterize this curve, right? In our case, that's why it's called uniform parameterization. Uniform means from prime numbers. In one span, it will be 0 to 1, which means the parameter t or geoparameter will be sits between the values 0 and 1. a lot of them. They're kind of like a geometric ruler for the actual calculations. And you're going to think about that as a snapshot in time, mathematically speaking, or in space, if we geometrically speaking. So the t parameter 0, it means that we are calculating the point for the curve in the beginning. And this point will be the loudest one. Then this one, less loud, less loud, less loud. They have the same loudness, but from the perspective of the t parameter here, depends on which one is closer, has the maximum effect, right? And that's how the curve is constructed. At every given point of t, the basis functions basically defines which one at the t parameter is the loudest. And we're going to see that we have a cumulative sum of them. So the c of t is actually a position. This is a position. So the position of the point, which will be interpolated then. So the position of point, and we're going to have a lot of them once again, this is the domain, at every given point is a sum of the basis functions multiplied on their corresponding points. Every single one of them does these calculations for all the points which are in effect. Well, this is true for the single span. It will be a multi-span surface, then their effect will be limits by the span. But it's not important now. The concept is still the same. So that's why this geometric domain, or TGeo, I'm sorry, is so important. And as you can see, all of these parameters are necessary to actually construct as this t parameter, or t geometric parameter, which actually defines the geometric ruler, the actual ruler through which curve will be parameterized and constructed, right? Okay, what is this then? The parametric domain. You see, as I said before, you don't have control over the geometric domain, even though, I can go into this curve, right? I'm gonna type what again, and you're gonna see, even though that I don't have geometric domain, I have parametric domain. It says 0 to 180, right? I'm gonna change this, and I will look again, and it is the same domain. So when the surface, the domain, the parameters, the vector nodes, the t value, the t geometric value, they set up in the process of construction. When the surface, the curve already constructed, you can't change that. It's already built in, because you're gonna see by moving control vertices, I'm changing the curve, but its parameterization stays the same. And as you're gonna see, even though that I don't see the geometrical domain, which, trust me on this one, it stays the same, parametric domain didn't change also. So what is parametric domain? Well, because we can't modify parametric domain, doesn't necessarily mean we can't remap our curve and ask the curve to specify its parameter at every given moment in time, or in terms of the geometry at every given position in time. But we can't say, please give me values at the specific t parameter. I don't know them. And I don't have access to them because I don't want to be able to change them. But the parametric domain is something you not only can change, and in most cases you should, this is something which system gives for you to ability to map it the way you want and specify the values at this parameter and points, vectors, and so on and so forth in basically in the linear measurement you want. Let me actually explain it in a different manner. Imagine that you have a rope, right? You have a rope. Now starts from 0 and ends somewhere, right? Can I measure this rope? Well, yes. How I want to measure that? Well, depends. Maybe I am in United States, right? And I operate with empirical system, right? So I have a measuring tape or a ruler, right? So I can measure the distance. So let's say that if I am American, not always, well, of course, it's just an example. I can measure that in inches. Let's say it will be X, and I will get some value when I measure the rope. Now, the rope exists, right? It's a physical object. It has specific properties like type of a material, thickness, etc., as well as length. So I'm measuring this length and I'm measuring in inches. I will get number, right? Now imagine that I'm not in America, I'm not in the United States, I'm in Russia. And we are not using, instead of a, empirical system, we're using metric system. So I can measure the same rope in a with different numbers. So for me, it will be like, millimeters, right? For example, right? It will be y. And I will measure the rope using my measuring tape or a ruler, and I will get myself a different number, right? So these numbers are not the same, but the rope is still the same. You see, the rope didn't change. It's just the way how I measure it is different, right? Let me give you the last example. Imagine I'm the lone survivor, right? On an island, on an empty island, right? And I have a rope, and I would like to construct a raft, using this rope and try to escape, right? The problem is that I need to find the middle of this rope, but I don't have a ruler or measuring tape. Instead, I have a stick. What can I do? I can measure it with a stick, right? Like this. Just take my stick, plug it a few times, see how many sticks, fit inside, right? And I'm gonna figure out, okay, so the middle, right, will be like a 2.5 sticks, or 2.7 sticks, or something like this, right? And that will be the value z, right? So they'll all amount like 1, 2, 3, 4, 5, like 5 sticks, right? Let's say it's a z. So it's not the same as y, it's not the same as x, meaning that measurement is relative, because our systems of measurement is relative. Depends on what's your measurement, right? I can measure it in bananas, I can measure it in elephants, in whatever I want. And this parametric domain is basically give us an ability to specify the ruler. Like you have a curve, like I have a curve. I would like to specify this curve. I can't use the original geometric domains because I can't change that. But instead, what system does, it looks at these values and gives you a different domain, basically remapping the values. It doesn't change them. It just uses a factor to represent one set of numbers in another set of numbers. For example, the concept of normalization, which we used when we constructed the grid, is the same concept. Right? So I can represent the numbers from 0 to 1 to the new domain with a specific factor from 0 to 100, right? Or numbers with the domain of -3 to 5 to the numbers of 7 to 6. If I wanted to do so, 6 to 7, if I wanted to do so, it's just a different multiplier. And that's what it does. It basically, the system, and this is standard and universal approach for all the CAD systems, it gives you this additional ruler and does it automatically. The only problem is it doesn't know what kind of a measurement you want. What is your measuring tape? So it tries to predict things. And that's why I said in the beginning that this is the number x. I don't know how it represents these numbers through this set of numbers. And it really depends on a system. It depends on a tool even, and where the object can construct it in space. So this x can be a quarter length. It can be the arc length. It can be the cumulative sum of the quarters between the control points. It can be differences between planar positions between the beginning and the end. It can be anything. System tries to predict, but it doesn't know. So it gives you something it predicts and tells you that you can change that if you want. So what it means in the practice is that now I have a ruler which I can use to not only measure my curve, but specify the point on this curve and everything which comes with this point, like tangent vector, curvature vector, and so on and so forth. So this parametric domain, or this measuring system, is actually T, parametric. This is what it is. Very important property. So we don't see this, but we see this. So it means that I can really specify something at, like, let's say that I would like to specify something in the middle, right? And it gives me the domain, for example, from 0 to 100, right? So it says that this curve parameterized from 0 to 100, right? So the middle, where will be the middle? Well, at 50, right? So I'm gonna say, please give me point at 50. Can you do that? Systems will answer that yes, it can. And what it will do is it will take your t parameter, which you specified, like figure out what's at 50. Then it goes back to this domain, see where it is. It's like in the middle. Then it goes in and use the factors to go back to our original geometric domain, see what TGeo equal to your current value here, right, your 50 in the t parameter, right? So it's all connected. And then it goes into the original formula. And if you asked for the position, it just, because it is a position, it just calculates the function at the given t, but not the one you specified, but the one you specified converted to the actual one in the geometric space, which once again, you don't have access to. And it gives you a position, meaning it gives you a point. And if you want, at this point, and because this is the function itself, but you can figure out the derivatives of this function. For example, at this point, at the same t parameter which will be converted to geometric parameter, I can calculate the first derivative, right, of t. That means that the t is already calculated, and which will be a speed. In mathematics, in curves, it will be a tangent vector. Tangent vector. It can be a curvature, right? Or in mathematics, it will be acceleration. I remind you, this is the basis functions. And by the way, the sinus and cosinus, which we explained earlier, are actually basis functions as well, just a different type. So acceleration, and that will be the curvature. And it will be, you know, a third derivative, a fourth derivative, and so on and so forth, if you have enough degrees, of course, all right? So that basically means that the construction of the curve automatically maps the curve for you to use and analyze. So when I'm saying the process of mapping, the actual process of mapping is already built in when the curve is constructed. But if we want to capitalize on the mapping, we need to specify to the system what kind of information I want to get at the specific parameter, which is a parametric domain on the curve. And once again, we are right now talking about the curves, but a little bit later in the session, we'll start talking about the surfaces, right? And actually, before we talk to the surfaces, let's actually look at how it works in practice and what all of this gives us. And to do that, in Grasshopper, first, I need to bring this curve into the Grasshopper. How am I going to do that? Well, I use some nodes, which basically give me an ability to take this curve and toss it into the Grasshopper so I can operate with that. The problem is that Grasshopper doesn't hold geometry. It can't do that. All the geometry is in Rhino. It's not in Grasshopper. Grasshopper can only stream. Right now, we are streaming. When we built the script, we streamed from Grasshopper to the Rhino. Right now, we want that it not only stream from Grasshopper to the Rhino, but from Rhino to Grasshopper and from Grasshopper back to Rhino. And for that, we have a very specific set of nodes. I mentioned them a couple times, I believe in the last lesson, in the previous one, I'm sorry, and it is time where we actually can address them. And there sits under the parameter tab of your main palette under the geometry subcategory and primitive subcategory. You're going to see they are very similar. They even have the same generic shape of a hexagon, right? Let's start with the geometry. So this set of nodes give you an ability to stream data in. And as you're going to see, it has a very specific names: point, vector, circle, curve, plane, rectangle, mesh, you know, field, even a lot of stuff like subdivs, whatever. It basically the type of data you want to stream. You need to specify this type of data. There is even geometry which actually can eat everything, right? So let's try to stream this curve into the Grasshopper and from Grasshopper back to the Rhino. Now, what kind of nodes I need to use? Well, it is a curve, right? So circle is not the one, point is not the one, curve, that is the one. Do we have anything else which can help us here? Yes, there is another one which is called geometry, because this is any type of a geometry. Let's start with the curve. I click on the curve and plug it in. Please note that this node has an input. We won't be using it right now, but this is a very important observation for later. So I will select the node. As you can see, it's yellow, means it doesn't have information. I will right click and I will pick set one curve. I pick set one curve, and as you can see, Grasshopper minimizes itself. Just give me an ability to specify the curve. So I'll go in, hover on the curve and click. Now a few things happened. First, the curve become green, and it will become green if you go to the top right corner and make sure that this icon is selected. We'll talk about that later. Just be sure that it's turned on. This is the type of visualization, right? So that's turned on. We visualize the curve which we plugged into the Grasshopper, and then it streamed back to the Rhino, right? If I click away, it disappears, right? No, you're gonna see this curve in the Grasshopper is the original curve. This one is the streamed curve, and when I deselect, like it hides itself, right? No, if I will click on the original curve and hide it temporarily, to do so I will type hide and hit enter. You're gonna see that underneath actually another curve, which is a red one. What is this curve? Well, this is this one, just not active. This is basically a curve, the original one, which was streamed to the Grasshopper and then streamed back into the Rhino, right? So now basically can operate with that and it will change. And the original curve, let me type show again. Oh, sorry. Oh yeah, here it is. This original curve will stay intact. It's just the original curve from the Rhino, it will not change. Now this bridge is live. And actually, let me prove it that this is the bridge. If I will click to the panel and figure out what's inside, it says referenced planar curve, and it references the original one. If I will select the original one and hit delete, that's it. It's broken now. There's nothing there because the reference curve is no more. So this curve is here. I can just hide it to visualize it from the Rhino, but as you can see, it's still there. It knows where to look, right? And of course, as I said, it's a live link. So if I'll pick my curve and I will move it somewhere else, as you can see, its streamed version will follow, right? It samples it and then push it back, because I can do something with this curve, modify that, and then it will be visualized here in the Rhino. And this is true not only for the curves, it's true for absolutely any type of data you stream from Rhino to the Grasshopper. So this is universal approach, okay? Now, I mentioned that there is another node here which we can use, and this node is the node called geometry. Now, this node actually has a container for everything. This node contains only the curves. This one can take everything. So once again, right click, set one geometry, pick on my curve. This is the curve, this is the same curve in the different nodes. If I will check, as you can see, it's identical. The difference is the geometry can eat everything, not only the curves. For example, I can go in and plug a couple points, right? And you will be surprised or not, I don't know, but points in in Grasshopper and Rhino, points in Rhino are actually represented as geometry, even though mathematically speaking that's nonsense, right? It's just a point in space described by free vectors. But it's actually a good idea. So now we have this geometry and we have this geometry. All of that is geometry, right? So if I'll go in, right click, set multiple geometries, select everything and hit enter, you're going to see that when I will inspect it, you're going to see that there is quite a large geometry inside. A curve, we already have our curve, right? This curve, and 3 points, 1, 2, 3, or 1, 2, 3, I don't know the order. So if I will try to do the same with this node, which basically picks only the curves, I will fail, and it will show me only the curve, not the points. Now, why it is important? Because we're going to use these nodes on top of each other to specify the type of data. For example, remember that I said that it has an input as well. And that's not a coincidence. If I'll open up my geometry and I can use the same nodes which I used to bring geometry, and I can use them to specify the type of a geometry if it's already somewhere, like it sits in some kind of a type of node, right? So if I will use the node called point, right, I can right click, set points if I want, or I can use it to effectively filter the list, right? And specify what kind of a data I really want from this. They can be here, they can be hidden within the actual point or the actual curve, like for example, coordinates of vectors, domains. We'll talk about that a little bit later, like everything. So if I'll plug it here, you're gonna see it's red, yes, but if you look here, you're gonna see that now it's effectively sorted me. Now I see only the points, right? And the curve, you know, is not a point, and it becomes to be a null. And if I will if I'll clean the tree, I didn't explain you this node. This is the first time you see it. Don't worry, I will talk about that later. You're going to see I can assort it, remove the null, and now I get myself a points, right? Here you go, my points. Now this is very important construction because these nodes not only give you an ability to import data, but they have an ability to toss the data and specify the type of data, right? Now before we move on, there is another subcategory of that, or another group or subgroup, which is called primitive. Now this is called geometry, this is called primitive. And it's basically self-explanatory. Geometry defines the type of a geometry, have an ability to import geometry. Primitives don't have an ability to import geometry, but they have an ability to specify the type of primitive data. What is a primitive data? Matrices, Boolean operations, numbers, domains, data, a lot of other stuff, like integers, right? It specifies the type of data. Let me quickly show you before we actually go to the practical example. So imagine that I have the two numbers right here, multi-line data. Now, what is it to you? Is it an integer? Is it a number, or is it a string? Well, you may say 0 and 1. This is definitely a number, right? And some of the nodes in Grasshopper understands it like, yeah, this is a number. That's for sure. I know that this is a number, but not all of them. On top of that, I can represent these numbers as something else. For example, Boolean operations, right? What is Boolean operations? True and false. There is a specific relationship between the number and the Boolean, like 0 equals false, 1 equals true. I hope you know this. Can we convert that, or not convert, but represent it for the different type of data? Yes. We go to the primitives, we create Boolean, this node, bring it in, and instead of a 0 to 1, it will be treated as false and true. So this is the node which extracts specific parameters of data, or represent the data for the different primitive structure, right? Here is another example for you, the same 0 to 1, and this is actually the example from the previous lesson where we use the average mean, right? Average mean. And I said that I will explain it later, and this is the time. So if I'll plug it directly, you're going to see it give me an error, right? Nothing here. Why? Because this node doesn't understand that in panel you have numbers. It treats it as a strings. If I will use sliders instead, it will understand that. But the panel, it does not. I need to help the node to specify what it actually looking at. And it's looking at the numbers. This is the numbers. 0.5, average mean from 0 and 1. Perfect, now it works. I specify the type of data, it works. So as you can see, these two types of nodes are actually pretty powerful, and the ability to import geometry is not the only property of them, and we'll be using them along the course down the line, and I'll be using it quite often for the different situations. So we will encounter them multiple times, and I hope you will get used to them eventually. So these are out of the way. Let me now delete that because I deviated from our task, and we'll go back to our curve. So now we need to visualize this stuff and how the mapping actually works in practice. So this is the curve, right? Now this curve has a domain. We kind of click and type what, and we're going to see that this domain from 0 to 180. I remind you, this is a parametric domain. Can I visualize it in the Grasshopper? Well, we already actually know how to do it. We go to the primitives. We'll set up, pick the domain. Which one? These or this? These or this? Curve. Domain, one number. Let's try this one, right? We will talk about the two-dimensional domains a little bit later. And yes, indeed, this is the same number, right? Once again, what? 0 to 180.134. Well, it's like just round with a little bit different precision, but the concept is the same. This is the same domain. Right, so we have an access to the domain. We have access to the curve. Do we have an option to say that we have the value between 0 and 1, like 90 in the middle, and visualize something on this curve? We have the curve, we have the domain, we need to have something which can specify the number with this domain and visualize values on this curve. And we have this node called, wrong node. This node called evaluate curve. It locates under the curve analysis. Here it is, evaluate curve, right? So if I will use my curve, you're gonna see this is the first input. The second input says parameter. What parameter? t parameter. So this is the pool of our parameters, our domain, and we already talked about that, effectively a pool of t parameter. So I can plug the value. Which value I want it to be in the middle? Let's say 90, plug that in. Look at the curve. Let me just kind of delete this place. Look at the curve. Yeah, it's somewhere in the middle. And you're going to see I will start changing the parameter. You're going to see that it basically calculates by default the point, right? It is c of t. It is a position, right? It calculates me the point for which the curve was constructed. It's a coincident point, of course, right? And not only that, I said we can calculate the derivatives from that, like speed, acceleration, or tangent vector, curvature vector. Look at that. What is this? Oh, this is a tangent vector at this parameter, basically an arrow. I can even visualize that. Let me just quickly visualize. So this is the point. Let me just increase the amplitude. Don't worry about the amplitude and stuff. We will talk about that a little bit later. We'll be using that as well. So I'm just quickly visualizing. Here is the vector, right? This is the first derivative, you know, speed, in our case, a direction, right? Once again, we were able to do that using our parameter and use a derivative, right, from the basic formula. But we can do the second one, the acceleration. Why not? Let's do that. So we go into the curve analysis and we'll look at the curvature here. Same things, plug the curve, plug the parameter. Look at, now it will give me the oscillating circle. The story for another day. This oscillating circle, this is a representation of a curvature through the radius. It's not important. Here is the vector. This is our curvature vector. I can visualize it like this as well. Will not spend your time on that. You get the point, right? So we're gonna sample that at the curve. So that's basically, we have a mapped curve, and its mapping comes from the t parameter, which is a parametric domain, which actually the values of a geometric domain represented for the new domain. And we can change these pools to whatever we need, and we will change in the next lessons. For now, just remind you, we can change it in Grasshopper, we can change it in Rhino, but not today. Just know that we can change the scale. We can change, like, what will it be? Inches, millimeters, sticks, bananas, and so on and so forth. Just later. All right, these out of the way. Now when we understand it, how the what is the mapping of the curve, and now you realize that the mapping already done for you. You just need to properly read the data, and you can remap that if you want, as I said. Now we're gonna look at the surfaces. Why we started with the curves? Well, because surfaces can't be constructed without the curves. Curves are the basics, and the surface, the curves are the base, and the surface is a consequence, right? And there are no exceptions. No exceptions. And if you tell me, well, Alex, I actually go in, oh, this is the old curve, let me delete this. If we, you know, go on into the perspective mode, and you're going to say, hey, Alex, you know, there are a lot of tools which can give you an ability to construct the surface without the curves, and what you're saying is bullshit. No. Now, yes, indeed, you can. Like, for example, I'm using this tool, right? It is a planar curve through 4 points, right? And I construct myself a curve. Did I specify the curves through 4 points, right? Here's the surface. Did I specify the curves? No. But doesn't mean that the system didn't construct them. Also, no, it does, because it is important. Through specifying the points, system automatically constructed me a 1-degree curves, which means basically a straight line. Then does all of that, calculated the basis functions and so on and so forth, and eventually get me to the surface. So curves are origins, and I would like to explain you why in details, because once again, we are interested at mapping the surfaces, not the curves necessarily, but the algorithm is very similar, at least at the beginning. So let's dive into it. So as I said, curve, the origin of a surface is curve. How many curves we need? Well, we need at least 2 or more. It can be 4 curves, 5 curves, 30 curves. Like, for example, it really depends on the instrument. Maybe you want to do a rail, right? When you have 1 rail and 25 how it's called, oh my god, generation curves, right? So there can be a lot of curves, right? but the surface will become four-sided. You'll quickly realize why in a second, and you have a pool of curves. The minimum amount, as I said, is 2. Let me visualize a very, very simple example. Imagine that we have two planar curves, right? One goes in this direction, right, like this. Another one, let's say, goes in this direction. Okay. Imagine they may not be straight actually. We may think that it is straight. It may be curved, but from the top they straight, just to simplify things, right? Now curves, we already know how the curves constructed and through what they described. Now imagine that a curve has a few control points, like for example, first, second, third, and fourth, right? 4 control points, right? And this curve, just for the simplicity, they're not necessarily supposed to be identical in quantity. But let's say that it has the same 4. 1, 2, 3, and 4, right? So 4 control vertices. Now every control vertice has its correspondent basis function. Let me visualize it here. First, second, third, fourth. I'm using crosses for that, right? So first, second, there are 2 of them in one place, so they're coincident. So first, second, third, fourth. Okay, so how the surface is constructed for them? Well, in 2 big stages. Stage number 1, which has nothing to do with the NURBS geometry in general. It'll be the NURBS mathematics, let's put it this way. So first things first, system will construct a matrix of control points which are missing, right? And it constructs that through the amount of them it constructs through the cross product, but the actual positions I will not tell you because depends on the tool. Rail, sweep, loft, patch, whatever it is, they're different. Some use the straight linear interpolation, some use it only on the edges like here, and the inner ones are different. I will not specify. It's pretty heavy duty mathematics. It's not connected to the NURBS actually. So they are just the points, and not just the points through which surface is supposed to be constructed by a control points. So they are not necessarily supposed to go through, right? So as I said, this is a cross product, and this is a matrix. What is a matrix? Matrix effectively is a grid, right? Pretty much the same as we did in our script in the beginning, which describe the position of an element in the grid for 2 numbers, right? The number in column, the number in a row, the number in column, the number in a row. This is called matrix, and we can calculate these matrices through the cross product. What does it mean? You take the value, these one, and you take all the R values for that. So basically this is basically for every, like for example, one component you get all the list of another's, and so on and so forth, and so on and so forth, and so on and so forth. That's how you get yourself a matrix. That's what the cross product actually is. All for all. How many of them it will create? Well, the squared amount, right? Squared amount. So we'll have these one, we'll have these one, we'll have this point. We're supposed to have this point, this point, this point, this point, this point, and this point, right? So all are the points which a system constructed. Once again, it did not only construct it as a matrix, which every single one of them will be described by like 2 numbers, like for example ij, right? One of them is row, another one is column, doesn't matter, but it's within the matrix already. It's the proper grid, right? So, but they're just the points. They are sitting where they're supposed to be using additional mathematical algorithms, depends on the tool. How about the surface itself? Well, we have a problem here, because if you remember, to construct even a curve, you need a basis functions, right? Do we have a basis functions for these points? No, we don't. What we have instead, we have 2 curves which forms the side, in our case, over a surface, right? And we have basis functions only for them. What we're gonna do? Well, that's where the actual NURBS mathematics come into the play, and the process of creating basis functions and actually constructing a surface called tensor product calculation, or tensor surface product, or some people call it tensor product surface. It's not important. So basically what happens is that it will construct the system will construct another matrix using cross product as well, but this time it takes all the possible combinations of a basis functions. What does it mean? It multiplies as one basis function on another, these on these, these on these, these on these, these on these, and so on and so forth. So every basis function here we should get, and because of the cross product, we will have the same amount and same description as the original point. It will be the same matrix with the same indices, right? The amount of rows and amount of columns, they will be correspondent one to each other, right? So we'll have the same amount of them using the cross product, right? And I remind you, this is a multiplication of the basis function. And what is the basis function here and basis function here? This is a basis function at a t parameter in a specific power of a curve. So this is the origin of our surface, and it's already built in. I'm just multiplying the parameter basis function at one parameter, multiply the basis function at another parameter with a specific degree. They can be different. I'll get the result here. And now for every point, we have all the necessary components, because this, at the end of the day, what we need to do? A sum of them. So basis function point, basis function point, basis function point, so on and so forth, so on and so forth. So the actual result will be the sum of them. But there is one key difference. We actually already constructed the curve at this point. But there is one key difference. This is a matrix. It's described by two values, not one like a curve, right? Curve was described by a single parameter. But here we have two directions. It is a two dimensions because we have a matrix, and there are two t parameters for one and for another one, which are used in calculation. Meaning that the point in these two, the actual parameter and the surface, of course, has geometric domain, and it, of course, has parametric domain. Concept is identical. It will not show you this, it show you this, it give you ability to remap it, but it's not one domain, it's two domains. One, because of the basis functions here, and basis functions here have a different t parameters, it basically described by two of them. Every single one of those, it's a multiplication of them. And this is a matrix. So we have two domains, and we even have names for them, as well as for the curve. So the curve domain, like for example, let me visualize, this is the curve, right? And it has our t parameter, right? T parameter, which kind of goes like where it's supposed to go. We have a name for that. We call it U, or U domain if we talk about the full domain of a surface. Full U domain. Curve have only one, U domain. Surface has two directions, right? One of them will be U, another one will be B. There is, of course, a specific relationship, which one is U and which one is V. We'll talk about it just a little bit later. Now, to visualize this stuff, imagine that you have a table, right? Like a table, right? It's my God. You have a table, right? Now, a table has a surface. The surface of a table, right? The actual top part. You want to measure that, right? You have yourself a ruler, right? This time you're not on a distant island. You have yourself a ruler. You can measure that. How you measure that? How you get the proper values? Well, you measure it 2 times in the one direction, right? And in another direction, right? So you get a length and width, right? That's the same. It has 2 directions. It's just one of them called U and another one called V. And we have 2 numbers, right? Makes sense? So this is, at this point, this is already a surface already. Already, this is the surface. So, last important thing before we get to the practice is the actual values of a parametric domain. Because as I said, when we constructed the surface, we have a geometric domain. We don't have access to that. Instead, system will construct me a new domain. When we constructed the curve, it tried to predict which describes it the best, basically creating ourselves a ruler, right, which we can change. But for the surface, it's not the case. Why? Because the system already have parametric domains for its components. We have curve, we have multiple curves. What it does, it inherits the actual domains of the curves. Let me quickly show you. Imagine that I'm gonna have, go to perspective mode, or maybe to the top view. Let's go to the top view. Now imagine that I'm gonna have a couple curves. Let's say the first one, And let's say that I have the second one, like an example here I show you pretty much, right? Like this. Okay. And let me construct a surface. So for that, I will use the sweep command. So I will type sweep. Now this is my rail. This is my profile curve. Hit OK. I create myself a surface, right? And this is indeed the surface. If I look at the perspective mode like this, right? Makes sense. So if I'll click here, you're going to see that I have an option to pick the curve, right? If I'll pick the curve and I will type what, you're going to see that I have the domain from 0 to 149. Once again, we can change it, we will later. 149, what's about this one? 147, let's now check the surface. 147, 149. You see, it just inherits the parameter domain or the actual rulers from its base components. Simple as that. All right. Now, let's talk practical solutions now. So we are going back to our surface. I will just actually keep this one, right? So to the surface, once again, the surface is already mapped, right? It mapped by the system already. Same with the curve. How can I capitalize on that? We already know that we can specify the point on the curve. How are we going to specify the point on a surface? Well, we need to bring surface in. How? You already know how. We go into the parameters, open up our geometry tab, and look for a surface. Where is this? Surface or geometry. We already talked about that, right? I'll bring surface this time. Click on the surface, right click, set one surface, click on the surface. Look at this, it's green, it's our surface. Let's check it out. Okay, we have a reference surface. Can we visualize that domain? Yes, let's do that. Primitive. This is a one-dimensional domain. This is a two-dimensional domain. It is a two-dimensional domain. Let's plug that in. Look at that. We have U and we have V directions. One of them is U, one of them is V. I will show you how to understand which one is which a little bit later. So one of them is U and one of them V. Now remind you that when we analyze the curve, a mapped curve, we use the node called evaluate curve, right? This one. Do we have something for the surface? Yes, of course we do. It's called evaluate surface. Let's go in, type evaluate surface. Here it is, right? Now as you can see, it's a little bit different. Now input is logical, curve, surface, makes sense. Outputs we'll talk another day, but here the second input is different. The first one for the curve called parameter, and it was logical. Yeah, we have a t parameter, our local domain, logical. Here instead of a parameter, it says give me the point. What point? Now if you hover here, you will notice that it's actually very specific. It says UV coordinate to evaluate. What is UV coordinate? It is a value of U and V domains of the surface. Why it says UV coordinate? Because UV domains for the surfaces has another description or the name. It's called UV coordinate space as a local space of geometry, specifically surfaces or meshes. So it's just a different way to call the same thing, a different name for the same thing, right? But yet it's very specific. It literally says give me a UV coordinate to evaluate, and literally says that this is a point. Now technically this is not true. Coordinates mean coordinates. I can literally give it two values, one and another one, and it will eat it, and it will represent me the point or first derivative, second derivative, the normal direction, the u direction, v direction, and a lot of other parameters at a given point, solving the derivatives for the function. And it's actually will be a little bit more complex than that, but it's not important. But how can I plug these two values? You know, if I will go in and I will plug, like, for example, value 20, and like it starts from 0 to 149, 0 to 147, 20, 20, and try to plug it in, nothing will happen. It will give me an error. Why? Because it looks for the very specific syntaxes. It looks for the syntaxes which looks like this. Or alternatively, if you will, or it's not important. You understand this, the curly brackets are important for that. All the syntaxes is important for us here, right? How are we going to do this? Well, we're going to use the concept which we did in the previous lesson where we used concatenate, right? We get numbers, we get our curly brackets, manually combine everything and so on and so forth to get ourselves a number. We can do the same and then plug it into the input point and it will give me the proper positions. But we can actually plug the point here. And this is very, very cool. Think about this. Imagine that we construct ourselves a point. So I'll go and I will type point. Oh, no, not this one. It's just the bypass node. So construct point. All right. As you can see, by default, we have a point in 0, 0, 0. We already learned that, you know this. You actually can predict what's inside, right? So if we analyze this, right, it gives me the proper syntax is 0, 0, 0. The only problem is that point here are 2 numbers, and this is 3 numbers. But a part of that syntax is correct. If it will be only 0 with 0 with curly brackets, it will be exactly right. And Grasshopper is smart enough to know this. And when you plug a point and it literally says, give me the point, it looks at this, it will automatically chop the third value here. It will get only 2. To prove it, let me go in and bring some values. Let's say 100 and 100, right? 100 and 100. This is our point. Let me actually gonna move this stuff somewhere here, right? So this is our point. Now, if I will use this 100, 100 in the point, it will show me the actual function will show me the point on a surface at u100, v100, right? Let's go and try it out. Let's plug the surface into the surface, point into the point, and here we go. This point is now represented on a surface in its coordinate space, UV coordinate space, or within its UV domain. You can call it either or, it doesn't matter. Now, as you can see right now, it's actually a little bit more complex. We have like a grid on top, we have X and Y axis on top, a lot of other stuff. It's what these nodes give you. All of that is really important and really cool. We will talk about that later. For now, I want to visualize only the point. How am I going to do that? You already know how. Geometry, point, bypass, pass me only the point data, hide this one. Here it is, my point. And as you're going to see, if I'll start moving that, you're going to see, for example, this is the value 0, 0. If we go in, you're going to start moving. You're going to see it can't get to the end. Why? Because the maximum is 0 for our sliders, and the maximum is these ones, right? And actually, if I will increase the value beyond the limit, it will just interpolate itself away from the curve, trying to predict where it's supposed to go. But it's a really cool property, but this is the story for the future session. All right. So if you think about that again, this is actually amazing because what we did is we took a coordinate in Cartesian coordinate space and were able to map it using or visualize it on a mapped surface using its domain. And now we have the representation of this point on a surface, right? And this is relative. So if I will construct not 1 point, but 2 points, or 3 points, or 4 points, or grid of points, which has a very specific relationship between each other, and use them as my points, what will happen? If they are within my domain, and once again, we're gonna change this, and we can change our parametric domains, it will take all of that and map it on a surface. Because the surface is already mapped with the proper parameters, because we already have the t parameter there, right? That's the beauty of this. This is the base concept of how surfaces are mapped and how you actually can take a primitive data in Cartesian coordinate space and map them on the surface. Now, before we finish this lesson or this session, one important thing is that, and I would like to mention again, you don't necessarily need a point. You're going to construct the values without visualizing the points here or constructing the points. You're going to bring 2 numbers with a specific syntaxes. That's it. But it's just easier and in practice, very, very useful, right? This is exactly what we're going to use in the future. Or at least the base functionality of that. The core functionality, not the core functionality of that. Modify it with a lot of other stuff. But apart of that, one important thing, there is a very specific relationship between U and V domains or UV coordinate space and Cartesian coordinate space. So as you're going to see, the X component and the U component, when I plug them here, it actually served specific values. So one of the X become to be U of V and Y become to be U of V. Which one which? We agreed upon this thing a long time ago, and this is a standard for all computer graphics and science and everything. So X component is always related to the U direction, and Y component always related to the V direction. There are no exceptions. We agreed on that, and this is what it is. And in fact, if I will go into the, let's say, perspective mode here, let me just kind of hide this. Now, sometimes I just want to hide something, right? And just so that the Grasshopper temporarily doesn't visualize me anything, because I have a Z buffer effect right now here, right? Because of the tessellation. So what I'm going to do is I'll go to the top right corner, and instead of this icon, I click on this one. It basically hides everything Grasshopper has, can visualize. This one will be outlines and points, and this one will be geometry. So I'll click on this one temporarily. I click on my surface, and I will type dir, which stands for direction. Hit enter. And you're going to see now this is an option to change the direction. We will actually use it later. But for now, you're going to look at the colors. And if you look closer, you notice that the colors are very similar, red and green. So X direction for any point or Cartesian coordinate space and red arrow here, they actually link together because the red is U, and I said the X related to the U and Y related to the V. That's why U direction is red and Y the U direction is red and the V direction is green, right? So now you're gonna see which direction is which. We can flip it, we can swap it, we can reverse it, we can do a lot of stuff with this, but that's the story for the future. What's important is now we know how CAD systems map curves and surfaces that we can have, even though that you don't know yet how, but you know that you can remap the surfaces to your own domains, and you can represent primitive data like points from Cartesian space on the actual surfaces using these domains and UV coordinate space of a surface. Alright guys, that's it for now. Thank you very much for watching, and I will see you in the next lesson.